done curve sketching. Just a little summary. I've got a take-home quiz for you, a little group quiz. Excitement galore. So, what are we going to do every time we're asked to graph something completely? We're going to find the x-intercepts and y-intercepts. That's something you could do from previous grades. So if possible, sometimes the x-intercepts will need technology, but if you can find them, plug in 0 for x, plug in 0 for y, and solve. Okay? Another thing from previous years, look if your graph has any asymptotes. You're going to have vertical asymptotes whenever you have a non-permissible value. You're going to have horizontal asymptotes when x gets really, really big and it approaches something. So you sort of have to do a limit as x goes to infinity and a limit as x goes to a negative infinity, or you have to look at the graph and say, we interrupt this lesson to remind students that during class time, they should be in class. But don't go in the halls. Probably. It's supposed to snow again next week. Did anybody see that? No. Yeah. Then we go through the calculus part. You find your first derivative, and the number line. We'll find all your local maxes, local mins, and your stationary point of inflection. You find your second derivative, you find where it's equal to 0, you draw the number line for the second derivative, and you can find where it's concave up and concave down, and your inflection points. So this is the calculus part. So steps 1 and 2 is sort of like, what do I know about this graph from previous years? Does it have any intercepts that I can find? Does it have any asymptotes? Then we go to our calculus part. And in that calculus part, when you do that number line, you're going to naturally find out where it's increasing, where it's decreasing. And when you do the second number line, you're going to fill in the happy face. Right? Find out where it's concave up. Oh. Right? This is the fact that Jack didn't know until now that it was Friday. But this is how he's feeling now that he knows that it's Friday. And then you just have to sketch the curve. All right. So, do you want to do a little review, put some in, or are you ready? Do you want to just, yeah, let's do some. Okay? We had sort of these types of functions, polynomial functions. Were you able to find your x-intercepts? Maybe. Uh-oh. Did I not make that one animate? No, it's supposed to animate. There we go. X-intercepts of 0, -2 and 2. Found your derivative. And solved for it and got plus or minus 2 over root 3. Not the most beautiful point. And if you got those points, you could use your calculator to plug them into the original equation. Is it okay if I scroll down to here? Or is that too far? No response. That's okay? Or go up a little bit? You're good? So you could either type it into your calculator and get 3.07 and negative 3.07. If you did it in your head, you would get 16 over 3 root 3. Oh, I love the kindness in this class. It's so refreshing. Good? Can I scroll up to look at the second derivative? You're working on it? Again, I would probably label this number line. I'd put a little f prime beside it. Second derivative, a much nicer inflection point. Can you give this to Abby? And now you can draw it. You've got your x-intercepts, you've got your max, your min, you've got your inflection point. Apparently, it's really important to draw the point negative 2, 0 very big. Like, that's a more important x-intercept compared to the other ones. So again, you find your x-intercepts, maybe. There it is. Plus or minus square root of 3 over 3 over 5. 5 over 3. Wow, does not a worst looking 5 ever? Anyways, it's 1.29. Find your derivative, factor, find your points, and you get nicer points, but you have a stationary point of inflection, which is kind of interesting. Find your second derivative, some not as nice points. You could still factor out the 30x, but then you have a 2x squared minus 1. When you solve that, you get x is plus or minus 1 over root 2. The inflection points are not as nice values. And put it all together. So we got from this green inflection point, concave down, then concave up, then concave down, then concave up. You get the inflection points from your second derivative, where they're equal to 0, but then finding the y-coordinate, again, anytime you're finding a point on your graph, you're finding that by plugging it into your original graph. All right, start the next one. Okay, preliminary stuff on the rational function. Did you find the y-intercept and the x-intercept correctly?
Oh, I forgot about that.
Did you find the asymptotes correctly? There's a non-permissible value of negative 2 on the bottom. That would make you divide by 0, so that'll be your vertical asymptote. Your horizontal asymptote, what happens when x goes to infinity? Can you see that the same power on the top and the bottom, the limit would be 3 over 2? That's right. All right, there's your derivative. It's simplified nice. Did anybody simplify it? Why is it important to simplify it? Because it helps you when doing your next derivative. Now, the thing that sometimes gets forgotten in this one, so once it's simplified, you get f prime of x is 10 over 2x squared. That's never equal to 0. So I have that in green here, that it never equals 0 because the only way a fraction equals 0 is if your numerator is equal to 0. But when we make our number line, why did I include the negative 2? Because it's a non-permissible value and it's an asymptote. So you always have to include your non-permissible values on your number line. And in this case, this graph in each section is always increasing. In our second derivative, I would probably bring my 2x plus 4 squared up to the top so that I could do an easier chain rule. And my second derivative is negative 40 over 2x plus 4 cubed, also never equal to 0, but you still need to put negative 2 on the number line. I did the chain rule way and not the quotient rule way because it's nicer in this case. Pretty nice results in this question, no number 26. So when you go to graph it, you can label your x-intercepts and y-intercepts. You know where your asymptotes are. I added another point just by plugging in negative 3 to see where it was to get positive 4. But you would know which sections things are in because of the increasing part of the graph. Do I need to scroll up at all? I can do this. Is that, oh, that's probably really small. That is good? Okay, we're good? For this next one, I'm going to set a domain restriction for you. If there is a domain restriction on your graph, that means you also have to label the endpoints. What happens at negative 3? What happens at 1? Preliminary stuff. 0, 0 is the y-intercept and also the x-intercept. And it's the only x-intercept because the only place that 2x e to the x is equal to 0 is if x is 0. E to the x is never 0. Maybe put that again. Put that in there. And here we'd also need endpoints, so I plug in negative 3 and get negative 0.3. I plug in 1 and get 2e, or 5.44. And there's your derivative to see if you got it right. Endpoints, negative 6 over, no, it is negative 6 e to the 3. Yeah, and it's over e to the 3 because he plugged in a negative 3, which would be over e to the 3. Negative 0.3. Because it's just an arrow saying that's as a decimal. Because sometimes when you're like, where should I put this point on the graph? If you've got negative 0.3, you like, I have an idea. If you have negative 6 over e cubed, you're like, ah. Yeah, well, you'd be pretty close. I'm always able to guess a lot better after I put it into my calculator. Okay, now I'm going to guess. Yes, did you find the points? Yes? It's 0.74.
Oh, I was right.
There. And then your second derivative? Right, you're going to have to do another product rule. You could either use I used the factored one, so it was only, and it could be factored out again. And now you get x equals negative 2.
Oh, what?
All right, so now that you've got your inflection points, you could put them all on. You have endpoints, so you would actually lose marks if you kept going here, right? I've got it dotted because that's what the graph does, but you'd actually have to end it at those endpoints. Mm-hmm. Let me know when you're done, and I'll put the graph back up. Use this one, it's better. I'm going to skip the next one because the next one's calculator. And if something is calculator, well, then you can just type it into your calculator and find everything. So it's kind of defeats the calculus purpose. I mean, you could show some work with your derivative, but you need to graph this equation anyways to solve it. So that's where I'm going to leave that last one. I'm going to